So as you guys know, we're working on contingent claims AMMs. We actually benefited, we're very lucky to benefit from having a large team of very productive, intelligent, motivated people. So it's actually been a real pleasure working over the last week with everyone. And we actually, we set our ambitions pretty high, and we didn't, reach all of the goals that we set for ourselves, but we actually made quite a bit of exciting progress. And I think we have to make sure to give credit to everyone on our team for that, and also to special thanks to Sylvan and also Patrick McCory for being generous with their time, having discussions with us throughout the week. Okay, next slide. So I'll just go through this very quickly because we've discussed this a few times throughout the week. So contingent claims are assets that give their owner a claim to a specific state-dependent payoff in the future. Automated market makers are protocols that quote buy and sell prices for a particular asset without having to match buyers and sellers through a limit order book. And a contingent claim AMM is an automated market maker that sets prices for contingent claims. And so that's what we are working on this week. Next slide. These are, as we've mentioned, we think having these capabilities is really powerful. Having trustless AMMs that can price contingent claims and maintain solvency when the claims come due can be really powerful in building out applications like insurance on blockchain, not just pricing options, but like we said, some kind of much larger and kind of more fundamental economic infrastructure components like property damage insurance, health insurance, and so forth. So that's why these are important. Next slide. So we kind of split up our objectives into two main objectives for this week. We wanted to, there's two kind of critical components of the contingent claim AMMs that we wanted to hone in on. The first one is being able to implement a hedging portfolio. So in order to cover the liabilities that come due for the contingent claims created by an AMM, you need to essentially hedge the risk dynamically that those liabilities represent. So the first kind of main goal that we set for ourselves was to implement a hedging portfolio on Ethereum that obtains these positions in the underlier to hedge exposure to options by interacting with Uniswap. And we also talked about being able to do this on layer 2 settings like Arbitrum in order to reduce gas costs, really. So the second main vector of attack we wanted to focus on was to be able to verify kind of complicated off-chain computations. So for actually doing the pricing calculation for these contingent claim AMMs, the computational demands are kind of much more intense than what the blockchains can currently handle directly. And you need to do things like Monte Carlo simulations. There's just not really a clear way to kind of do that on chain. So what we need as an important ingredient for building out a trustless AMM is a way to verify these computations that were done off chain in some way that's analogous to the way that they're verified when they're done on chain. So those are the kind of the two main angles we pushed forward on, and so now I'm going to tell you a little more about our progress on each of those. Next slide. Okay, so this is kind of an overview of the kind of two pieces that I just described. So let me first describe one of the pieces, the off-chain computation piece. So how would this work in practice? A user is going to be interacting with an API through a web app. They're also going to be tied to an external account that lives on Ethereum. When they want to acquire a contingent claim from a contingent claim AMM, they're going to send a price request to price that contingent claim to an API. And we want that API call to be verified in some way. So the API is going to live next to or along with an SGX enclave. This is the approach that we ultimately decided to take, and we can discuss a little more about why we think that was the right approach at this stage to take. So the API processes the price request, actually does the pricing computation on the SGX enclave. The enclave returns not just the result of the pricing computation, but also a signature that allows the verifier contract on Solidity to confirm that the correct code has been run in order to produce that particular price. So that's one of the main pieces, verifying these off-chain computations, and that's kind of an overview of how the circuit works. User makes call to API, API actually does the computation through the Enclave, and then the Enclave updates the blockchain. So the other piece that is important that I mentioned was the hedging component. So if we think of there being a delta hedging contract associated with the contingent claim AMM, it is going to be responsible for holding positions in the underlier in a way that's analogous to keeping their the total exposure to be essentially zero net delta. So as new contingent claims come in, or as the underlier value changes, the exposure of this reserve-based delta hedging contract will change, and it will need to update its position in the underlier. So this is the on-chain interaction between the reserve-based delta hedging contract and the Uniswap wrapped ETH USDC contract. And so the way this works is when the price of the underlier is updated by through users interacting with Uniswap, Uniswap makes an emission. The emission is picked up by the off-chain resource. The off-chain resource asks the API, which sends it to the SGX Enclave, to calculate the new delta that reserve-based hedging contract needs, sends the request or sends the response back to the contract, checks that it came from the correct Enclave, and then picks up the actual hedging position from the Uniswap contract. So those are kind of the two pieces that we're going to be, that we were focusing on for this week. Next slide. This is a little more detail about how the SGX Enclave works, how we're thinking about it working. Again, this is something that we kind of just familiarized ourselves with over the past few days. So I think we kind of honed in on something that works, but it's certainly we're open to suggestions in terms of ways that this could be made more efficient. So the main idea is you associate an SGX Enclave with some particular source code. Then you initialize it, the Enclave, at that source code. That generates a public key. And then from the public key, we can pull out essentially a pseudo address, a pseudo Ethereum address, and feed that into a smart contract. Then when the SGX Enclave does computations, when it sends the result of the computations to the blockchain, it can also send a message signed by the private key associated with this public key. And then on chain, we can check that signature corresponds to the pseudo address associated with that particular Enclave. So this is kind of the verification step. So that's the way we're thinking about it now. Next slide. Okay, so this is just a screenshot of the output of the initialization step for the SGX Enclave associated with the Black-Scholes calculation. And I think, so as I mentioned before, the Enclave produces a unique public key for each version of the source code. So this is what's important. This is just kind of illustrating that step. I think Preston might want to jump in and say a few more specific things. Preston Roswood, who actually contributed greatly along with Sylvan to actually implementing some of this code.
Yeah, so basically I just want to talk briefly about what we're showing here. So the first thing that we see in the screenshot is the Intel attestation service response, which is basically just proof that we're getting remote attestation from Intel and we're not just doing it locally. It's not that. So in order to do that, you need to build a quote which contains information about the source code and about your Enclave. And then you give that to Intel and they give you a response. And as part of the response, you get information like your public key associated with the MR Enclave. And you get to check if that MR Enclave actually matches the source code that you claim it's from. And then at the bottom of the screenshot, you can see that we get our public key that's associated back from Intel, and we're able to parse it, and we can use that to sign messages and check if whatever has been signed is actually associated with this message. Okay, so this next part is explaining or showing the code for how to actually call and interact with the Enclave. So the screenshot on the left is the price API. And basically this command will open a sub process and just type this into a terminal, essentially. And so here we're basically saying that we want the app to run this sign protocol where the Black-Scholes price happens to be a part of it. And you get your output in the BSM out and a signature as well in the BSM.signature. So that part is just from the API able to call the Enclave code on the right. And then on the right, we have our, not all of it, obviously, but a chunk of our Enclave code. So the first thing you see on 67 is, or on line 67, is the result of getting a put price with some fixed variables. Of course, these should be, decrypted from some input data, like in a file from the API or something. But unfortunately, we didn't have time to implement that. So yeah, you compute the price of this put option, and then you have to, on line 70 and 72, you have to convert the result into an array of bytes so that you can sign it on line 84. And so now you have the result of your Black-Scholes pricing, and you also have the signature of it, which can be written to a file and can be read and verified on chain.
So now I think the next step is so that was kind of the off-chain verification circuit. That was the progress we made along that dimension. And now I think Daxi can show us a live demo from his console about how the hedging contract works that we were able to implement.
Yeah, you would have to unshare your screen and I will take over.
This is a 3-minute warning, guys, by the way.
Yeah, can you guys all see my screen? Just want to make sure.
Yes.
Yeah, I will make this quick. So this is the on-chain component. There are 3 smart contracts on-chain. The first one is the raw smart contract, the router smart contract, and then the next one is the verifier, and then the last one is the reserve, which serve as the actual hedging portfolio. And the router would be serve as a middleman. So whenever the off-chain request comes in, it will first verify the request is from a trust source, and then it will call the hedging portfolio to do rebalancing. And here's a live demo. And you are looking at the left top corner. So I will just launch a local testnet forking the Ethereum mainnet. And then the second console would be just deploying the contract onto the testnet. So yeah, we just finished. And then the bottom right is the price simulation. So what I did here is I wrote a script to interact with the local Uniswap to kind of like simulate the buy and sell Ethereum within the range of -50 and 50. So I will run that for now, and it will take like 10 to 20 seconds for it to start running. But yeah, and once you've started, you will be able to see the pre-trade price and also the post-trade price return from Uniswap. And then lastly, the last terminal on the bottom left is the rebalance simulations. So we actually make a call to the router smart contract and then give it a delta, and the router will connect to the actual hedging, the reserve smart contract, and do the rebalancing. So as you can see, the left side, it is started to do the rebalancing. Like let's say the delta is -0.49. You can see after the rebalancing, the reserve, the Ethereum in the reserve actually decreased by that amount. Yep, and yep, that would be it. I will pass it to Edward. How do I unshare my screen? Thank you. Thank you.
Okay, I'm going to try to rush through the rest of it. So basically, we chose this as just a standard model, like Patrick said. It's tractably yet still statistically sophisticated, so we could do things like try different off-chain trustless methods to try to verify those statistical computations. And it gives us an explicit way to compute those hedging portfolios in the case of options. So what's the lesson here? Should you hedge your bets or more is better? That's just a meme. I'm going to throw it out there. I'm going to skip the model in terms of BSM. I'll spare you guys the mathematical details. This is just computational details. And I also wanted to just really briefly let Colin and Robert discuss this taxonomy, which they did, which was very, very useful for us to kind of get an idea of what the lay of the land is. And you guys can actually see more. This was a decent amount of work. And there's also a Google Doc. So I'll let them take it away.
Yeah, we can just talk super fast. The main purpose of this was mainly to break down different option protocols into like the core fundamental differences and just get a very good layout of what's existing out there right now.
Yep, that's exactly right. You have AMMs, order books. Within AMMs, you have Black-Scholes reserve ratio models.
Okay, awesome, guys. I'm going to move on in the interest of time. One of the things that's really important, like we talked about, is these computational challenges. Monte Carlo simulations in ML are not feasible really to implement on chain right now. So trustless computation appears to be the short-term solution. Maybe ZKPs in the future. There are some future directions that we're currently considering. These are extensible as well to insurance markets. The idea that you can hedge is not always available in insurance markets. They rely more on idiosyncratic risk. But hedging is still an important aspect of things when it comes to commercial paper, to credit default swaps, to options, to a bunch of financial tools that are very useful and have not, as of yet, not been implemented on chain, at least for other than maybe a couple examples. So this particular direction on indifference pricing allows you to actually incorporate the unhedgeable risk. So this first component here, this delta.s, that's how much you can hedge. L is the liability. And then that's the cost. CT is the cost of trading. So in this particular model, what you're thinking about is the certainty equivalent. If I'm going to write on this liability that's going to come due in the future, how can I hedge this? If I can't, how much would I require in order to be comfortable to cover the liabilities that are going to come due in the future? So this encapsulates both of those. And the main difference I just want to emphasize between, spot market AMMs, which is what you see with most of the protocols that are out there, and something like contingent claim AMMs, is that there's this time difference. You make a promise now for an obligation in the future. And one of the primary objectives of what an AMM should accomplish is being able to cover those liabilities in the future. And that's where the forecastings come in. That's where these statistical models come in order for us to get a sense of what that distribution looks like of future outcomes. And that's why it's so crucial to have these, very complex, heavily statistical tools at our disposal. And that brings me to my last point here, which is intelligent market makers. And this is kind of the frontier of being able to consider both hedgeable and non-hedgeable risks for contingent claims. And this in particular is using deep reinforcement learning. There's a great paper called Deep Hedging that's out there if you guys want to kind of pick this up. And it is something that you can implement with automated market makers as the entity that are quoting these prices, and then using a portfolio to hedge or just to assess the risk of unhedgeable claims, and then charge a price today for that.
And specifically, SGX can handle that. So that's one of the reasons. Yeah.
Yeah, well, we kind of skipped over that, but trusted hardware it seems to be the short-term solution for that. And there's a lot of other work that we actually did that we haven't had time to talk about. We transformed our Black-Scholes Merton into a ZKP friendly arithmetic circuit. So we did approximations on it and stuff like that. But we ultimately ended up going with SGX because it's more extensible. So this is our team. Thank you guys so much, everyone involved, and the judges, the organizers. And as you can see, we kind of hijacked Sylvan there for a bit to help us on the SGX stuff. Once we thought, well, after we saw his presentation, his wonderful presentation, and he was very, very generous with his time. So we also included him there with a little help me chat bubble. But thank you guys again to the team and everyone at IC3.
Great presentation. When can I ape into the token? I'm just kidding.
Awesome. Just for the sake of time for the judges, if you want to put your questions into the chat, then
Okay.
I think the team could like answer it async, in an async manner.